Hi everyone, in today's lesson from Unit 2, we'll be taking a look at our first geometric proofs. So this is notes number 3. So we're going to start off with some things that you should be familiar with from Algebra 1, but it's probably been a while since you've thought about these things. So in our left-hand column, that's our hypothesis, or the if portion. And then we're going to try to make a conclusion in the middle column, and then in the far right column, we're going to try to give a reason like why we know it's true or how we know it's true. So for example, in the first one, right here, if we take a look, it says if x minus 5 is equal to 10, then we know that x is equal to 15, because we know that we could add 5 to both sides of the equation to solve it. So that's an example of the addition property of equality. In the next scenario, if we take a look, we have 7x is equal to 56. Now if that's true, you know you could come in and divide both sides by 7 to arrive at the answer, x is equal to 8. And what I used there was the division property of equality. And you can abbreviate. I'm sure your teacher will let you abbreviate at least a little bit. So division property of equality. Alright, on to the next example. We have x divided by 5 is equal to 6. So we can multiply both sides by 5 to arrive at our answer, x is equal to 30. So the 5's divide out on this side, but essentially we're multiplying both sides of the equation by 5 to solve it. So that's an example of the multiplication property of equality. Okay, in our next example, if 7 times the quantity of x minus 12 is given to us, so this is the if, we want to take and distribute that 7 to everything in the parentheses. So we know we can rewrite this as 7x minus 84. And that's an example of the distributive property. Okay, one more example from algebra. This last case, it says if x plus 6 is equal to 9, then we know we can subtract the 6 from both sides. I almost gave away the answer. Subtract 6 from both sides gives us x is equal to 3. So that's an example of the subtraction property of equality. And again, I'm just abbreviating the word property to prop. Okay, so back to some things that we've taken a look at in geometry. In this next box, it says a equals b and b equals c. So let's just add the word if in front. If a equals b and b is equal to c, we will have to think of a conclusion. Remember that b is the bridge here that takes those two quantities and kind of holds them together. So as a result of these two statements, we can make the conclusion that A is equal to C. Now, typically we would refer to this as the transitive property, but because there's an equal sign, we could also have said substitution. Substitution is only a property of equality, so I can only use it when we have an equal sign. Okay, let me scoot this up a little bit. Okay, our last three are definitely from geometry this year. The next box, it says, if B is the midpoint of AC, so keyword being midpoint, then we should know that a midpoint divides a segment into two congruent segments. So a logical conclusion that would follow is to say that line segment AB is congruent to line segment BC. And to justify it, we would say definition of midpoint. So when you're working on proofs, it's a good idea to have your list of definitions, theorems, and postulates handy as a reference. Okay, in the next case, it says if ray ln, it's a little hard to see the little teeny tiny arrow on the end, whoops, but we have ray ln bisecting angle MLO. So if it's bisecting this angle, then it divides this angle into two congruent angles. So our conclusion would be to say angle MLN is congruent to angle OLN. And that's by definition of an angle bisector. That's what it does. It divides an angle into two congruent angles. Okay, last one. In this last case, and I'll scoot it up even more because we're going to see how many different conclusions we can make just off of this picture. One of the trickiest things in geometry is not having a lot of given information other than a diagram, and you have to figure out what to do with what you see in the picture. So in this picture I see two intersecting lines, and there are a couple of things going on. One of the big things that's going on is we have a pair of vertical angles that are congruent to each other. So I'm going to choose those two angles because they're numbered. Angle 1 congruent to angle 2. And we don't say definition of vertical angles, we say the theorem, which simply says vertical angles, that's really a G, are congruent. Okay, the other scenario that's happening here is that we have this angle 3, but when you combine it with angle 1, you get a straight line. So we have an angle that measures 180 degrees. So another conclusion could be to say the measure of angle 1 plus the measure of angle 3 is equal to 180. But check it out, it's happening over here too. So we could also say the measure of angle 2 plus the measure of angle 3 is equal to 180. And both of those are by the angle addition postulate. Okay, so next we're going to try our hand at some algebraic proofs. Well, when you write a proof, we do it in what's called two-column form. On the left-hand side of your proof are going to be what are called the statements. So I'm going to take a second and just write the word statements on this left-hand side. And the right-hand side, we write the reasons. Now, I know I wrote it in all caps. It doesn't have to be in all caps. Okay, I'm not shouting at you to write statements and reasons. Okay, with an algebraic proof, we start with an equation, and that's going to be our given information. Given information is anything that you're told in the beginning, either through the diagram or in actual writing. So when you take on an algebraic proof, you want to ask yourself, how would I go from step 1 to step 2? So if you notice, we start with 4x minus 5 equals negative 2, and then it changes to 4x is equal to 3. So just think about what you would do to solve it. You would add 5 to both sides, and negative 2 plus 5 is equal to 3. So you mentioned that you added 5 to both sides, and that's an example of using the addition property of equality. And you can talk to your teacher about whether or not you can just write addition. So next, going from step 2 to step 3, see if you can figure out what's going on there. We had 4x equals 3, and we know we want to solve for x, so we're going to divide by 4 on both sides. So dividing by 4 on both sides is an example of the division property of equality. Okay, let's check out another one. So we're going to take a shortcut here, and we're just going to say S at the top of the left-hand column and R at the top of the right-hand column for statements and reasons. So we have our given equation in step 1, and we say given and reason 1. And then you want to ask yourself the question, how would I get from line 1 to line 2? So if you take a look at it, what I did was I multiplied the left-hand side of the equation by 3 and multiplied the right-hand side of the equation by 3. So the 3's on the left-hand side divide out to give us 1, and we're left with x plus 7. And negative 11 times 3 on the right-hand side gives us the negative 33 in the next step. Okay, so we multiplied both sides by 3. So we were using the multiplication property of equality. Okay, finally, last step, to solve for x, ask yourself, what would I do? I would subtract 7 from both sides. So when I subtract 7, I end up with x alone. And negative 33 minus 7 is negative 40. So we got there by using the subtraction property of equality. Okay, let's take a look at another one. So one more algebraic one before we go on to the geometric ones. Okay, again, on the left-hand sides, give me an S for statements, right-hand side, an R for reasons. So we're given this equation, and if you notice, going from line 1 to line 2, I tried to eliminate this fraction. And how I did that was I multiplied both sides of the equation by 4. So let me just clean this up so I have some room in there. So I multiplied this side by 4, multiply this side by 4. And notice that I put it out in front, but I didn't actually multiply. It's there, but I haven't done the distributive property yet. So first, just eliminating the 4 on the left-hand side by multiplying both sides by 4 was the multiplication property. Sorry, it's iPad is acting up a little bit. So multiplication let's try that one more time. So multiplication property of equality. Okay, now I mentioned that we had that 4 out in front. We can certainly distribute in our next step. So get rid of those parentheses by multiplying 4 by 6 and getting 24, and by multiplying 4 by 2x to get 8x. So that's the distributive property. So notice the difference. I know that we are actually multiplying, but it's different than the multiplication property that we see in line 2. The multiplication property of equality, you have to show that you're multiplying both sides of the equation by the same thing. The distributive property, you're going to show that you're eliminating a set of parentheses by taking the number outside and distributing it to what's inside. Okay, my next step for solving the equation, I see that I have 3x on the left-hand side, so I'm going to try to move all the x's onto the left side. So subtracting 8x from both sides leaves us just with 24 on the right-hand side. 3x minus 8x on the left is negative 5x. That's equal to 24, and that was by subtraction. And it's a subtraction property of equality. And finally, take and divide both sides by negative 5 to arrive at your final answer. X is equal to 24 divided by negative 5. And again, I mentioned division. So we write division property of equality. Okay, that's it for algebraic proofs. Let's see what some geometric proofs look like. Okay, now for some geometric proofs. In number 4, it says we're given that line segment RS is equal in length to line segment PS. So you can mark those two equal to each other with a little tick mark. Then we're also given that line segment ST is equal in length to line segment SQ. And what we're trying to prove is that the whole segments RT and PQ are equal to each other, which makes sense because they're made up of congruent segments. So in line 1, we stated our given information. RS is equal to PS, and ST is equal to SQ. So go ahead and write given for the reason over here to the right. Okay, by the way, we should have at least an S and an R here for statements and reasons. Okay, going from line 1 to line 2, what's happening here is I'm taking RS and adding it to st to get this statement, rs plus st. And then I'm taking ps plus sq to get this statement. So if we have equal amounts, and then we're adding them to equal amounts, we're using the addition property. And it's the addition property of equality. Okay, and the next step, I'm asking you to identify what segments make up line segment RT. So check out RT. It goes from R through S to T. Okay, so line segment RT is made up of two pieces, and those two pieces are RS and ST. In the next line, we're going to do something similar. We're going to talk about PQ. Well, PQ, the line segment goes from P through S to Q. So we can say that PQ is equal to PS plus SQ. When you say that a whole line segment is equal to the sum of two shorter line segments, and all the points are collinear, that's an example of the segment addition postulate. Okay, if we take a look, now we're ready to do some substitution. Notice up here in line 2 that this says RS plus ST. And here we have RS plus ST. Sorry, I highlighted way too much there. RS plus ST is equal to RT. So what you're going to do is take RT and put it in place of RS plus ST. Okay, we're going to do something similar on the right-hand side of this equation. We have PS plus SQ. Down here we identify PS plus SQ as being PQ. So since PQ is equal to that sum, we're going to replace PS plus SQ with PQ. And we have what we were trying to prove, that RT is equal to PQ. So this last reason was by substitution. Okay, we have one last proof before you get to try it on your own. So number 5, it says we're given that the measure of angle AOC is equal to the measure of angle BOD. So here's AOC, highlighted in yellow, and here's angle BOD, highlighted in green. So let's put that in as our given information to start. Start with statements and reasons. So number 1, we're given the measure of angle AOC equals the measure of angle BOD. And again, that was given. In line 2, we're going to talk about what angles make up each of these two big angles. So AOC, and just a reminder, it's the yellow highlighted angle at the top there. It's made up of the sum of two angles, and it's made up of angle 1 plus angle 2 in the center. So you have the measure of angle 1 plus the measure of angle 2. Alright, take a look at the green angle. So the one highlighted in green in there is angle BOD. And notice that angle BOD is also made up of the sum of two angles. It's made up of the sum of angle 3 and angle 2. So I'm going to say BOD is equal to the measure of angle 2 plus the measure of angle 3. So when we talk about an angle being equal to the sum of two adjacent acute angles, or two adjacent angles, then we're really referring to angle addition. So our reason, or how we know these facts in line 2, is by the angle addition postulate. Okay, in the next step, I replaced AOC, the measure of angle AOC, in line 1 with this sum. And then I replaced the measure of angle BOD with this sum, the measure of angle 2 plus the measure of angle 3. So I came up with a new equation. So instead of using their big names, I set them equal to each other. I set the sums of the two angles that make up the big angles equal to each other. So that's using substitution. Okay, the next step, we notice that both sides have the measure of angle 2, which we want to get rid of. So the next step, we have to write the measure of angle 2 equals the measure of angle 2. And this is by the reflexive property. And I know it seems it's obvious that the measure of angle 2 is equal to itself, but we have to say that in order to be able to subtract it from both sides of the equation. So it's kind of like, oh, we really know this is obvious, but we got to do it anyway. So we're going to subtract the measure of angle 2 from the left-hand side of the equal sign, and we're left with the measure of angle 1. And on the right-hand side, we also subtract the measure of angle 2, so we're left with the measure of angle 3. Okay, so we use subtraction to get there. So we've reached our objective to prove the measure of angle 1 is equal to the measure of angle 3. Okay, good luck on homework number 3.